So welcome everybody to this very special event. This is a joint physics colloquium and a REYES talk. REYES stands for the Remote Experience for Young Engineers and Scientists. My name is Raul Briseño. I am an ODU physics professor and a JLab research scientist, and I'm also the chair of the co-chair of the REYES program. As you may know, REYES started as a summer program, and after its popularity, receiving over 7,000 registrants, we decided to continue it with a set of keynote talks throughout the year, and this is just one of those talks. Before I tell you about the speaker, let me say that we just opened the registration for this summer's program, meaning for 2021, and after less than 3 weeks, we have close to 1,000 registrants from over 70 countries. This summer, we have more talks, panels, classes, and we're even launching a mentor program. If you want to participate or you know somebody that may be interested, please share this information with them. Take a second to take a screenshot of this image. And in fact, we're going to put in the chat a link to the registration page. You can also use the QR code to take you directly to the registration page. While you do that, let me add that we have numerous speakers already lined up from local institutions, as well as from MIT, Berkeley, Dartmouth, and at least one very special speaker. If you're done taking a screenshot, let me just move on. As I already mentioned, we decided to continue having a series of keynote speakers. These are the lineup that we've had so far this year. If you miss any of these speakers, including some of the people from NASA and other institutions, don't worry. You can in fact go to our YouTube page and you'll find these talks as well as all the other talks and classes that we have hosted. What you should do is go to YouTube now and just look for ODU REYES. It'll take you directly there. And what you should do is also subscribe. The more subscribers we have, and helps us spread the word, and it helps us to keep this work going. So we appreciate that very much. Well, I'm very excited about today's speaker for many reasons. Her name is Zohra Dawoodi. Zohra Dawoodi, let me give you a little bit of background about her. She received her bachelor's and master's from Sharif University of Technology in Tehran, Iran. She received her PhD in 2013 from the University of Washington in Seattle, and shortly thereafter, she joined MIT's Center of Theoretical Physics as a postdoc researcher. She was not a postdoc for too long until she got a faculty position at the University of Maryland and is now also a Ricken Research Fellow. She studies strongly interacting systems such as hadrons and nuclei using analytical and numerical computational tools, including effective field theories like QCD, quantum simulations, and quantum computing. She's a very versatile researcher, and this is reflected by the fact that she has received numerous awards, which include the Ken Wilson Award, the DOE Early Career Award, and she's also an Alfred P. Sloan Fellow. But really, her greatest achievement is being able to share an office with no windows for 2 years with me while still managing to be friends after that. And the last 10 years, Zohra and I have written 7 papers together, several with her, just and me. We've had endless debates and discussions, and I'm very proud to call her a great friend. So today she's going to be telling us about efforts towards simulating laws of nature and implications for the simulated universe. Zohra, please take it away if I figure out how to stop sharing my screen. Okay, thank you so much.
All right, great. Thank you very much, Raul, for the very nice introduction and for inviting me to this very valuable series. I'm very glad to be part of it and be able to tell you about this topic that I think is very exciting to me. I'm sure it's very exciting to a lot of you out there. And it kind of the backstory is that as a physicist who is interested in simulating the laws of nature and be able to do first principle numerical studies of matter in the universe, And what does actually that mean for a simulated universe itself? So that's really the question that we want to get to the heart of. But in order to, again, motivate this very kind of philosophical oriented question, I would like to tell you about why I'm motivated to think about this problem. So let me start that by saying that if we are interested in simulating the laws of physics, we have to know what those underlying laws are that govern nature. And in particular, it turned out that 3 of the 4 fundamental forces in nature are described by a very nice, beautiful, and not too complicated mathematical framework that is called a standard model. What is this model about? Well, it describes the strong, weak, and electromagnetic interactions of all the elementary particles that we see out there as the building blocks of the visible universe. And what are these particles? Well, they are quarks and their corresponding antiquarks. So there are antiparticles also in this picture, but there are also leptons and they're anti-leptons. And there are also particles that are the carrier of these forces. They carry the effect of a strong, weak, and electromagnetic force. They're called gluons and photons and W and Z bosons. And fortunately, we are living at the time that all of these particles have been discovered in our experiments. So we proudly can say that we know for sure that this standard model is the underlying theory of interactions between elementary particles in nature. And in particular, at the heart of this picture is sitting the Higgs particle, which is the last discovered particle in the standard model. And it's the particle that is responsible for the mass of any massive particles that you might recognize in this picture or not. So that's the story. And it's quite amazing that finally this kind of the puzzle has come together, and we know kind of what governs the visible sector of the universe, at least based on this nice picture. But unfortunately, that's not the whole story. There's a big blob of questions out there that we don't know the answer to. They are, at the moment, mysteries to us physicists. And what are these questions? Well, we don't know what the nature of dark matter is, or what the nature of dark energy is. Why is that matter is so dominant compared to the antimatter in the universe? Why is it the gravitational force, which is not in this picture of a standard model, we don't have a quantum theory for yet? And why is it that it's so much weaker than any other force that we have been able to describe with the standard model? So these are the kind of questions that keep particle theorists and particle experimentalists, as well as cosmologists, keep them busy and excited in everyday research. But I want to argue that there is also another big blob of questions out there that are connected to a standard model. Basically, these are the phenomena that are occurring in the visible sector of the universe, which is supposed to be described by this standard model. But because of the complexities that arise, we still don't have a good answer or kind of good predictive capability to answer these kind of questions. And I tell you about what those questions are in a moment, but I want to say that these are the type of questions that would keep nuclear physicists excited and busy in their everyday research these days. So what kind of questions I'm referring to? As I said, one set of questions are really about how do the complexities in the visible universe emerge from the standard model itself? Because I mean, this is a simple picture of the underlying forces and fundamental particles, but how do they actually come together in a large macroscopic system and give rise to a lot of exotic and interesting properties of this kind of larger scale matter that we observe? Let me give you examples of this. Well, let's not go that far. Let's just think about a small subatomic particle, which is the proton, This is what is composing an atomic nucleus in the end of the day, along with the neutrons. So a single proton for a long time was believed to be sort of, in a simplistic picture, just 3 quarks, right, of different flavors. But what it turned out is that because these quarks are being bound together with the strong interactions in the standard model, the picture is not that simple. So this really nice artistic view of what the proton could look like is this really complicated sea of objects. And these objects are quarks, antiquarks, a lot of gluons, really a lot of them. And in the end of the day, if you are trying to predict or calculate what the mass of this object is or how its spin come about, then you have to compute all these complexities from first principles, for starting from these quarks and gluons. How can we do that, right? And this is really the whole point of when we talk about simulating nature from first principles, from the underlying interactions. That's to be able to get a complicated picture like this without having to make any approximations whatsoever. So that's the reason that we would like to do the simulations from first principle. Eventually, if we have enough computational power, you can even imagine to simulate directly from these standard model interactions that I was talking about, even very large astrophysical objects that are of interest to us. For example, the neutron stars, these very exotic, compact objects out there that we don't know what their nature of the sort of interior phases of this object is. Eventually, if we can simulate this thing accurately and properly, we would have the knowledge of what's going on in the interior of this object, or what would happen if 2 of these neutron stars would collide and, for example, create this interesting gravitational waves. We would be able to compute that, right? So that would be the power of simulation. But obviously, you can see that it would not be an easy simulation. What other interesting questions we can explore in this complicated sort of visible sector of the universe? Well, one question from sort of intellectual or philosophical perspective is how sensitive life on Earth is to the underlying input parameters of the laws of nature. Okay, let me make this a bit clear, right? The reason that we all are here and are breathing and are enjoying life on Earth is the fact that there are enough carbon and oxygen out there to enable this kind of life, right? So how do we get carbon and oxygen in the universe? It all boils down to the fusion of these helium nuclei. And in fact, they occur at a very precise rate such that it makes the production of these very essential elements of life, the carbon and oxygen, enough of them gets produced because of this particular rate, and therefore we are here. Now I can start asking the question of what would have happened if, for example, in these quarks and gluons of a standard model, which are really sort of the building blocks of nature, as far as we can tell so far, what would happen if we change their masses or the strength of their couplings? Would we still get enough carbon and oxygen for life to exist? Well, fortunately, again, that's the power of simulation. If you're able to perform a simulation using theoretical laws of physics, you have the ability to set the starting point of the simulation, this input parameters for masses and couplings, the way that you like, and then explore what the outcome of that simulation is. So you have some kind of power over even just performing experiments, because if you just go to the lab and measure things, you don't have the ability to change things that nature has already set for you, right? So that's another motivation for why we would like to do these kind of simulations. Another type of questions in this big blob of questions that are related to the standard model is the fact that if you're able to answer questions about the visible sector of the universe, eventually you also learn something about that other big blob of questions that are beyond a standard model, that are new physics that we would like to discover. Let me give you an example of why that's the case. For example, say we know that there is dark matter out there. Unfortunately, so far, we have not been able to detect any dark matter particle in our experiments. It has escaped our ability to discover them so far, but hopefully that would change with these ongoing large experiments on Earth that are trying to really detect these things. So how do these experiments work? You get a very large chunk of atomic isotopes, put them in some underground detector, and then try to just sit down and wait, and hoping that an incoming dark matter particle would come in, interact with your nuclei, and then you see some exotic signature that would tell you that, in fact, a dark matter particle showed up, and this is the nature of that particle. This is an example where you actually not only need to know how the nuclei and visible matter would interact and respond, but also how they interact with this new particle and new physics candidates. So that's very important that we would be able to do very precise theoretical calculations or simulations that involve matter, and it would be important to really connect this all the way to the standard model. So now you might ask, well, how? I mean, of course, it seems like, yes, we have a lot of reasons to go about doing these simulations. But what do we mean by simulation? How do we actually do this? That's an important question. So it is important to actually realize what the simulation is about, and to make sure that you all would understand what's different about the simulation of nature from fundamental laws that I just talked about, compared to the kind of simulations that you might have heard about out there. Let me give you a few examples. All right. So let's say that you're interested in predicting what the position of these billiard balls would be on the table if someone would give you the initial location of these, right? So you can run a simulation. The input to the simulation would be the balls, their locations, their velocity, and so on. Then you apply the laws of classical mechanics to run the simulation. And then you find the final arrangement of these balls on the table. So without even having to play, right, and find out what would happen, you can already know the answer if you run this simulation. And that's the power of simulation. So that's a simple example. You can imagine the application of simulations in other fields. There are very interesting projects out there when people are trying to simulate an organ. What do they do? Well, the input to the simulation would be the individual cells. Then they apply the laws of biochemistry or physiology. And then the endpoint of the simulation hopefully would be the organ, how it works, just like predicting, for example, how a given drug would act and maybe cure some disease related to that organ. So that would be very important. That would mean that we don't have to try these kind of medications on human subjects. If we have a very accurate simulation of these organs in the end of the day, then we can just avoid doing any lab work or clinical work. So that's really the hope at some point. But of course, this is very, very complex, and people are making progress, in fact, in this problem. What other simulations you might have heard of? Very famous example would be climate science, and try to predict the weather, right? So in this case, the initial temperature, pressure, and density of the atmosphere would be what you input into the simulation. Then you apply the laws of thermodynamics and fluid dynamics and so on. And what you get in the end would be the final temperature, pressure, density, and so on, which would tell you what the weather would look like tomorrow without having to wait another day to see what the weather would look like. So again, that's the power of the simulation. The question is that what do all these simulations have in common? And in my perspective, all of them are very important, very complicated, but in the end of the day, their level of complexity is nothing similar to what I'm going to describe, simply because these are all classical simulations. And I tell you what that means, okay? So basically what this means is that they apply the classical laws of physics. And we know that within the past century or so, there's been quite huge progress in understanding and going beyond the classical picture by realizing that really at the fundamental level, nature is quantum mechanical, but also relativity plays a role. So if I am claiming that I'm a physicist that is simulating nature from first principle, I have to ensure you that I'm also applying the rules of quantum mechanics and relativity in my simulation. So what does that mean for the simulation, right? So let me make this a bit clear. And in fact, this great scientist of the past century, Richard Feynman, told us how to think about quantum mechanics in a very intuitive way. This is what he told us. He said that imagine that you have a system that it starts from A and ends up in B at some later time. And then the role of your simulation would be to predict how the system gets from A to B and with what probability. Well, it turned out that if you just apply the rules of classical physics, there's only one single trajectory where the system can go from A to B, given the underlying classical laws. What about quantum mechanically? The picture is completely different. In fact, now there are infinite number of trajectories for the system to go from A to B. So if you want to tell me what is the likelihood that the system A ends up in system B, then you have to actually average over an infinite number of possibilities to get that number correct according to quantum mechanics. What is remarkable is that nature itself does this sort of infinite path averaging all the time. And it's just so amazing. And as scientists that are trying to simulate nature quantum mechanically, we should be able to at least have a good approximation of this infinite path averaging. And that's what we actually do. So that's one thing to keep in mind. Another thing is that, well, we know that also at the very fundamental level, we have to think about relativity. That's another departure from classical physics. And this is due to this other great scientist of the past century, Albert Einstein. And what the implication of relativity is for the physics of subatomic particles is the fact that now all these subatomic particles that I talked about in the standard model picture, whether they are quarks or electrons or antiquarks or gluons and photons and so on, they have some associated fields, okay? So this is an important context. To visualize these fields, just think about what you regularly think about fields, like the magnetic field of magnetized objects, like the Earth itself, or the gravitational field between the objects. So what this means is that actually to describe even a single elementary particle, you have to describe a field that expands over space and time. You can't just say, this is my particle, this single point, like you do in classical physics. We can't do that anymore, right? We have to think about the quantum mechanical and field description of these elementary particles. And that adds another layer of complexity to the simulations. And I'll get to that point later. But anyway, it turned out that if you include the quantum mechanical and relativistic description of subatomic particles, then you end up with a standard model. In fact, a standard model is called quantum field theory of fundamental interactions in nature. And that's exactly that mathematical framework that I was referring to in the beginning. This is really elegant, and physicists are very much proud of what they've built to really be able to describe nature based on this elegant mathematical framework, which again is based on quantum mechanics and relativity. So that's good. Now, given this quantum field theory description of a standard model, how can we simulate it? Which means that now I have the standard model. This is sort of the input to whatever I'm going to simulate, the visible matter, whether it's a proton or an atomic nucleus. And then you're going to use the power of the most powerful supercomputers out there to be able to perform this program of simulation, because I hope I convinced you that this is a very complicated, costly simulation compared to some of the things that you might imagine. So what kind of things we can simulate? Well, we can simulate nothing. And just literally, what this means is that if you're dealing with a quantum field theory, and you're dealing with a strongly interacting theory, like the theory of a strong force in a standard model, even the vacuum, which is like not having any particles or any nucleons, nothing, could be very complicated. And as you can see in this actual simulation that physicists have performed, and you can already see it right here, as a function of time, a lot happens in the vacuum because you have the gluons and quarks and antiquarks that kind of pops out in and out of the vacuum, and a lot goes on. So even the simulating nothing in these kind of theories is complicated and requires a lot of computational resources to enable an accurate description of nothing. Okay, so what about something like this complicated picture of the proton? Yes, sure, this has been done now. And we have a very good, precise description of the proton, starting from the quarks and gluons, that confirms what we actually see in experiments. So that's quite an achievement, given all these complications that I told you that you have to deal with to perform these simulations. Even more exciting, we can also make predictions for very complicated processes that are occurring in particle detectors, like in Large Hadron Collider at CERN, when you collide these highly energetic protons and you create a sort of jungle of things, and still using these simulations, you are able to sort of answer some of the questions about what you actually see in the detector and what they mean. So that's quite exciting. But really, I haven't quite told you how we do it. And in fact, because of this, another great physicist, Ken Wilson, and a lot of other great physicists that came after him to develop this program that he has started, we have the knowledge of how to simulate quantum field theories using a computer. That's a non-trivial question, right? How do we figure out to fit this problem into a computer? And that's what Ken Wilson started. And really, at the heart of the idea is the fact that, well, remember, you have to simulate these fields that extend over space and time. So even if you have a tiny patch of a space-time, you have to deal with infinite number of points inside, and there's no machine out there that can allow you to do this computation. So you better actually make your computation reasonable size to be able to use the power of these supercomputers. And what Wilson told us is to, well, discretize the space-time. You don't have to have a lot of these points in a small patch of the universe, as long as you have enough points to describe the physics that you're interested in, then you should be fine. And in fact, in the end of the day, you can take the limit where you recover the actual continuum physics. So that's nice. We also have to look at an infinite amount of sort of the space and time direction, right? So we can't have an infinite extent of these kind of discretized lattices, because then otherwise we have to deal with infinite number of points again. And we cannot fit that calculation. But again, in the end of the day, you should be able to find a ways to connect your theory to the infinite volume limit that would be the physical limit. So this has been figured out, and this is really the basis of what we do. And in fact, if you throw out hundreds of millions of hours of computations on the fastest supercomputers in the world, you should be able to achieve some of the things that I told you about in this program. And in fact, for example, with my collaborators, we're proud to say that we're looking at processes like nuclear reactions, like what is the rate of proton-proton fusion if you simulate this process from the standard model and things like that. So these are examples. And then at this point, when we are making this kind of progress, you start asking, well, I mean, what does that mean if physicists at some point are able to really precisely simulate nature from first principle? Why can't you just think about the universe itself to be a simulation, right? So that's kind of a very well motivated thought. And in fact, we're not the first people to think about it. And a lot of philosophers and thinkers in many centuries ago started to think about this question. And one of the well-formed arguments out there is due to Nick Bostrom, this philosopher in the UK, who came up with this argument. He said, well, assume these three prepositions, these three statements, okay? The first one being that human beings would go extinct before reaching a post-human stage. Meaning at some point, maybe 100 years, 1,000 years, whatever, we go extinct, okay? The second one is saying that human being will, this is being repeated. So the second one is supposed to say that the human being would never actually develop enough technology and power to be able to simulate its past, its own history, okay? So that's supposed to be the second one, which is wrong here in this statement. But then the third one, it says that we are currently living in a simulation. And here is the argument. It says that if you believe that number 1 and number 2 are not correct, then you should believe that number 3 is correct. And if you think about it, yes, that's the case, right? If we are able to simulate at some point our revolutionary history because of the technological developments, and we are not going to go extinct before reaching that stage, then why is that we think that we are not already in a simulation of someone else? That's very likely, right? So that's kind of the argument. But I mean, look, we're talking about a world of complexities. How could it be possible that 13-something billion years of the history of the universe might have been coming from the simulation? I mean, is it possible, like, is it possible that we human beings at some point reach the stage that we can actually do simulations of sizable systems? Let me argue that this is in fact the case, okay? Or at least maybe we're on the path. But there are some signs that we are making good progress in doing this first principle simulations. So here is how I put it together. So let's say that we want to simulate a brain, okay? And we are not going to simulate the brain from the quarks and gluons of a standard model, which is very complicated. Let's say that you're a physiologist or biologist, and you're just interested in simulating the brain based on the cell structure and neurons. And in fact, the number of synapses and their firing frequency that you have to include in your simulation is something of the order of 10 to the 16 to 10 to the 17 operations. So the way to make sense of these numbers, like 10 with 16 zeros in front of it, right? So this is a very large number, but just keep this number in mind. But then it turned out that if you had a computer that has the size of a giant planet, and you could use that as a resource for your computing, then that already can do 10 to the 12 operations per second for you. So you can see that a few of these planets maybe would get us there, right? But we should be also mindful of these other technologies out there that are going to revolutionize the computing, hopefully at some point. And in particular, if you have the power of the quantum computers at some point, as Seth Lloyd would put it, the ultimate laptop or the ultimate computer, then already a 1 liter, 1 kilogram computing machine that performs the laws of quantum mechanics to compute would have a memory of 10 to the 31 bits and a speed of 10 to the 50 operations per second. So it can have orders of magnitudes of these brains being simulated with it if we had such an ultimate laptop, right? So, well, maybe we can someday simulate the brain even from first principle. Would not be too far. But how far? Well, we looked at this question with my collaborators at the time in 2012, and we said, look, at the moment we can like simulate a few nucleons, right, or a small atomic nucleus in a very small volume of a space-time. So this is where we are now at the time in 2012. And then we looked at a number of other computations, first principle computations, starting from maybe 20, 30 years back. And we said, if everything would go as well in sometime in future, maybe in 50 to 100 years, we are going to be able to simulate lattice sizes that are of the order of even the size of a molecule or DNA or the size of the brain, even starting from the quarks and gluons. And of course, we are not going to be alive then, but someone else would. And it doesn't seem to be too far. And in fact, this is just the power of classical computers. If you are able to do quantum computing, then you can speed up this picture for sure, right? So then the question is, now that we think that Bostrom's second scenario is not likely to happen, and then let's imagine that we don't go extinct and we don't do anything bad to our race, and we are there until we see the point that we can actually do these simulations, then according to Bostrom's argument, it is likely that we are already ourselves being the simulation of some other entity, right? Okay, but I mean, this is not too convincing, is it? I mean, if you are an actual scientist, you start to ponder, how can we know, right? And this is my collaborators, Silas Bean and Martin Savage. This picture was taken a few years back. In fact, we started to ponder about this, not over a drink, so hopefully you don't attribute these thoughts to being drunk. But in fact, we were seriously thinking about, well, if this motivation is out there that the nature could be a simulation, as scientists, how can we rigorously go after the signatures of the simulation? We have to find these evidences before actually being able to say anything conclusive about whether or not we are a simulation. So that's what we did, and I'm going to just tell you very quickly, one of the things that we looked at, among other things, is the fact that if you look around in the universe, everything seems rotationally invariant. What that means is that if you take this picture of cosmos and just rotate it, actually nothing changed. And in fact, at the fundamental level, the laws of physics, or this standard model that I was talking about, is insensitive to how you rotate around and rotate your frame of reference. But it turned out that if you are in a simulation, and the simulation has the same limitations as our simulation of nature has, which I told you about, our limitation was that we could not simulate continuum. We had to go to this discrete space-time to be able to fit our simulation in a finite computer. Let's imagine that simulator of the universe is facing the same limitation. What would be the signature of it? And in fact, it turned out that you can go after this signature in a very ultra high energy cosmic rays that are coming to the Earth from all angles. And these are very rare. These have very high energies, but because they have very high energies, they're very sensitive to the fabric of the space-time. So even if there's a very small spacing with the point between the points in the space-time, then their orientation basically as where they propagate in the space and would tell us something about that underlying fabric of the universe. And this is a very technical picture at this point, but you can figure out sort of the surface of propagation for the particles, these high energy particles, if they are in a continuum space-time, as opposed to if they are on a lattice, just like we do our calculation. And based on this, we can put bounds on the lattice spacing of the universe, but we can also propose that if future experiments see some asymmetry basically in the propagation of the cosmic rays as they come to the Earth, you can detect sort of the underlying fabric, whether there's a space-time, discretized space-time or not, based on that information. And of course, that would be like one sign, sort of supporting the idea of the universe being a simulation. but it is not enough, right? We have to go out there and propose many, many different tests. And if these tests get confirmed, then we have built more and more evidence in favor of the theory of simulation. At the moment, we are not there, but that doesn't mean that we shouldn't think about it. This is really sort of the starting point of thinking about possible realistic experimental signatures that might someday build up and correct our knowledge of what the nature of nature is actually is. If you're interested in this subject, and I'm sure many are, you can check out this 2016 Isaac Asimov Memorial Debate that was hosted by Neil deGrasse Tyson. I was part of this panel. It was very fun. And I hear that many others also enjoyed it. So I would like to encourage everyone to also watch it if you are interested in 2 hours of debate over this by scientists and philosophers. And with that, thank you a lot. And I'm happy to take questions at this point.
Great. Thank you so much, Sarah, for such a great talk. We have a couple questions already. Maybe I'll start with the first one. This is an anxious and anonymous attendee asking, what kind of work would be left for us to do after we're successful in these simulations? I'd hate to find out that one day there's no questions left. What would you say to that person?
Well, that's very philosophical. I actually don't believe that one day we are left with no questions. I think it's hard to imagine. Even if we have the power of simulating, we never have an infinite power. That's for sure true. At least, I mean, in our universe, with our limitations, we don't have infinite resources of whatever kind. So I think there would be always things that would be unknown to us. I mean, one of the primary limitations that we have, for example, in observational science, is the fact that we cannot see far beyond. We can see sort of the past, which is limited by the speed of light, right? So at some point, everything would be dark and we have no knowledge of what's out there. And that sort of seems to be the future. The question is that can we already simulate it to know what's behind sort of where we cannot see experimentally? Maybe, but again, I can't imagine that we will have infinite power to do that at any time soon. You can then start to also ask about question of, even if we figure out what our universe is at the end of the day, by doing these simulations, can we also rule out the fact that there aren't other simulations? Maybe we are just one tiny simulation among many, many other simulations. Can you come up with tests to figure out whether there are other universes that maybe apply different laws and therefore the computations are performed very differently compared to what's being performed in this universe? I think these questions will not be answered anytime soon, so don't be discouraged.
So we can rest assured that we're going to have more questions left over by the time that we're not around.
Yeah, absolutely.
Sounds good. So Aja Harris is asking, could these simulations be used for unifying quantum mechanics and relativity?
Yes, very good question. This really goes back to what I described as the quantum field theory, being the mathematical framework that describes elementary particles and their interactions. That's exactly the framework that unifies relativity and quantum mechanics, if that's what you're trying to refer to. Basically, we have a way to make sure that both relativity and quantum mechanics are not clashing with each other in describing the subatomic particles. Unfortunately, we don't have that picture for the gravitational force. So we don't have sort of the quantum mechanical relativistic description of the gravity, particularly at very short distances of the order of Planck's distance. And that's still missing, right? So we have not been able to do that yet, although there are many, many ideas out there for doing that, but we don't have really a firm description like with a standard model for the other forces.
So at least we can have quantum mechanics and special relativity, but not quantum mechanics and general relativity.
Exactly.
Right. So Sebastian Kuhn, who's a colleague of mine, has a question. Perhaps we can see if he can answer it live. Sebastian, do you want to join us? Let me see if I can see if he can speak. I don't know if we can ask. Oh, perfect. Hey, Sebastian.
Hi, can you hear me?
Yep.
Hi, Surrey.
Hi.
How are you? I'm just trying to extend your curve to its logical limit. If right now we can simulate something with lattice spacing of 0.1 femtometers and maybe up to a few femtometers, just keep going. Eventually we reach a spacing of 1 Planck length and a size of the lattice of, say, 100 billion light years. And of course, we can't do this with classical computers ever. So obviously, we have to use quantum computers. If you put all of these things together, isn't that exactly a description of what nature is? In other words, the question whether it's a simulation or not becomes moot, because that's exactly what nature does.
This is exactly the way I think about it. For me, a universe could be just like a computational platform itself, right? As opposed to an entity that is running the simulation. We don't have to take on that kind of description, right? We can just think about the universe being already kind of a computational platform from the perspective of information theory. What is really interesting, though, to think about is that we don't know if the lattice spacing of the universe, if there is such a thing, would be of the order Planck lengths or smaller or bigger. In fact, what we actually drive in our study is that the limits, the bounds, the stringent bounds on the lattice spacing of the universe is already many, many orders of magnitude higher than the Planck scale. So we're not even there, right? I mean, some people believe that the underlying fabric of the universe is like just discretized at the level of the Planck scale, but we don't have the evidence for that yet because we don't have the enough stringent limit up to the Planck scale yet. And now this is this interesting possibility that maybe nature is not even Planckian, right? It could be that the gravity itself is classical. There is no need for kind of a quantum theory at the Planck scale because the fabric of a space-time is just is too coarse to actually get to the Planck scale. So that's another interesting possibility. Maybe our kind of lattice simulations don't have to go that far.
So I think we have a somewhat related question from another physicist that I'm going to ask him to join live. Alberto, do you want to, Alberto Accardi from Hampton University and Jefferson Lab has a question that perhaps he can ask live.
Sure.
Well, I will be glad to do that. Assuming you are hearing me. I had some problems with the microphone lately. Can you hear me?
Yes.
Okay, thank you for the talk. And my question is, but what about if space-time is really discrete in itself? So nature is weird, and we learned that with quantum mechanics. So the fact that the space is not as smooth as we tend to think now is not outside the realm of possibility. So let me say, if space-time is really discrete in itself, how can you distinguish that from your hypothesis that it is instead discrete because we are living in a simulation?
I'm not sure I understood exactly what you asked, but if what you're asking is that even if we discover that the nature is discretized, how can we actually distinguish that from the nature being a simulation? I mean, it could be that the nature is just discretized, but there is no underlying simulation. It's just discretized because it is discretized, right?
Yes, correct.
Exactly. That's exactly the point of what I said in the end of the talk, that look, I mean, there is this motivation out there. I mean, why is that the universe should be discretized? Maybe if it was computed and the computational platform is finite, then it would require such a discretization. But by itself, it's not enough, right, to either reject or accept this kind of hypothesis. We need a lot more evidence to be able to say a little bit more about the simulation. So I completely agree with this. I think we shouldn't get too excited, although that would be something that would support the theory of the simulation hypothesis. It would not be able to completely make it kind of an acceptable working theory of nature in the eyes of physicists. We need more evidence.
And
That other hypotheses cannot explain as well as this simulation hypothesis.
And do you have an inkling of what that could be, or a direction to go in order to get that?
I think now that people are starting to think about quantum computing as a way of computing nature, there are some interesting discussions and ideas coming right now that you can imagine if you had a quantum computer, what would be the limitation of that system? What would be sort of the quantum information theoretic aspects of simulation that you can actually explore in nature? And a lot of people, not just the sort of us, the strong interaction physicists, are thinking about this. Maybe not explicitly from the perspective of simulation hypothesis, but sort of trying to understand whether kind of nature is sort of a quantum information sort of related or structured thing, right? I mean, there's discussions of space-time itself having close connection to entanglement, entropy, and ultimately to quantum information. I think this is very deep and solid thinking, which is kind of related to this argument of simulations and computations, but not completely.
Thank you.
Sure.
We had another question from participant Steve, who basically was asking the same question. What is the difference between saying space-time is discrete and the universe being a simulation? And the way that I understand it from your explanation is that if we find that the space-time is discrete, doesn't necessarily mean that it is a simulation, but perhaps, that would be the most natural explanation given.
Exactly. It would be very intriguing, right? It would cause this other questions, why, right?
Right. Okay, so we have more questions. So let me read Sunil Porcarel's question, which is regarding the drawback. What are the drawbacks of classical simulations over quantum simulations and relativity? So, for example, people nowadays are doing classical simulations of biological and biological micromolecules. What can we say about these results and findings? And similar question regarding the simulation of accelerators in high energy physics.
This is a very good question. I should really clarify that all sorts of simulations, whether classical or quantum, are valuable, and this is the reasoning for it. A lot of times when you describe a system, you do not need to go all the way back to the fundamental level to describe that system. It would be an overkill. And the reason for that is that there are always effective descriptions of the system for the purposes that you're interested in. That would be good enough, right? I mean, if you want to describe the function of an organ, why would you want to go all the way to the quarks and gluon degrees of freedom to build a proton, a nucleus, an atom, a molecule, a DNA? That would be an overkill, right? What you actually need at that point is to just know the laws of biochemistry and physiology, and these are all basically understanding some rates of chemical reactions, for example, that are occurring at the physiological level, and inputting that in the simulation. That would be already good enough, right? So you wouldn't waste your computations to get something that you already know, but you start from something that you already know from experience or doing experiments, input that in the simulation, and at that level, the laws are just classical. If you're not thinking about subatomic physics, classical physics is good enough, and it's giving you the answer that you would be satisfied for the type of problems that you're interested in. So that's why I mentioned all these simulations in the beginning. to just say that they are very valuable. And in fact, they are doing it the way that they should be doing it. But because we are interested in different type of questions, and we have to start from this fundamental interactions. Again, because we are interested in different questions and different scenarios.
So we have several more questions, but I'll close with one last one, which I know is near and dear to your current research, which is by Nandita Sudha Tiwari from India, asking what is the current restrictions and problems that scientists are facing in developing new quantum computers. She lists changing the temperature as one of those challenges, but perhaps you can give us some insight into what are the challenges right now?
Okay, very good question. In fact, a lot of people out there are thinking about it, and a lot of agencies and from the private companies to government sector are spending a lot of money to actually answer these questions and go about sort of addressing these kind of challenges. So the answer to your question is really platform dependent. There are various different types of physical systems that scientists have proposed as candidates for quantum computers. You can use the atoms or superconducting circuits, or even more exotic objects like topological qubits. These have like systems with very different kind of physics and properties and so on. And each of them are coming with given challenges. I can give you one example from the platform that is closer to my heart, because I have a lot of good colleagues here at my institutions that are building this type of quantum computers. And these are the trapped ion quantum computers, where you trap the ions, you cool them down a lot, and you basically align them in a line, for example, and that then you can sort of address with the laser beams. Okay, so you have very accurate individual addressing of these ions. They're very small, but you can do that with the with the laser beams, and then therefore you can create quantum mechanical interactions and properties in the system. And that's why these systems are very useful for doing quantum computations. But then you are limited by scaling up this kind of system by because of many reasons, right? If you start to put a lot of these ions in the chain, these ions are interacting with each other with the Coulomb force. And if you have hundreds of these in a chain, you have a very complicated spectrum of the normal modes, if you know what that means, which in the end of the day means that the motional excitations of these ions in a chain would be very complicated mathematically to get right. But also that means that it would be very complicated to design the gates or these laser beams in such a way that you cleanly sort of address a single qubit to do the operation on them. So you have to go to other platforms. Maybe you can do a two-dimensional structure of these things and so on. So people are thinking very hard about how to actually do this scaling of various platforms. But I think the challenge is really maintaining the quantum coherence in the systems while you add more and more qubits together, given the fact that then you have a bigger experiment, bigger environment, more qubits that are talking to each other in an unwanted way, and you want to kind of destroy all of those things in favor of the type of interaction that you want in a controlled way. So this is really at the heart of the challenge. So temperature, all the sort of environmental noise and so on are going to be even more, the system will be more sensitive as it gets larger to this kind of environmental factors. So that's the challenge.
I think we could have invited you to give a whole another talk just on that question. So thank you so much.
I would be happy to if that occasion arises. It's a very fun subject.
All right, I'm putting you on the books.
Okay.
With that, thank you so much, Sora, for taking your time and being able to tell us about these really neat and cool ideas, which it's clear that it interested other people, and I'm sure many others. So
thank you very much. It was very fun. Thanks a lot for inviting me, and thanks for a lot of fun questions. I enjoyed it.
Great. Let me just remind people that if you, in fact, if you like this questions regarding quantum computing, quantum information, this summer we're planning to have a series of speakers on these concepts. And so this is just a gentle reminder that if you haven't registered yet for the REYES summer session of 2021, please do so. The link has been shared with you. So go ahead and do that. This is the closing of today's talk. We do plan to have at least one more keynote speaker before the summer session. So stay tuned for that. All right, everybody have a wonderful day, and I'll see you later.